Okay, let's get going. How's milestone 3 going? Is everybody here, the people who are in good shape for milestone 3? Is it good? So-so? It's going okay? All right. Well, onwards to milestone 4. Okay, so we were talking last week about heuristics that we could use to solve this computationally hard problem. We're calling it the traveling courier. It's like a variation of traveling salesman. And one of the things that we found is that if we used our milestone 3 pathfinding function that you guys are currently writing to kind of evaluate every travel order that we're interested in, it just takes way too long. So we have to use something faster than that. And one of the ideas that we came up with is, well, let's use geometric distance. Let's just say how far away are these intersections from each other. Let's assume we can go directly between them. And this will be reasonable, but it won't be perfect. And then if we do this, it's fast enough. And at the very end, when we've got our delivery order, we'll just call your milestone 3 find path function a much smaller number of times to just connect together our chosen delivery order. And that would work. Okay, so this is a reasonable thing to do. But it's not going to be perfectly accurate. Your travel times won't be, well, they'll have some error in them. They will correlate some with the real travel times when you're optimizing delivery orders, so definitely much better than nothing, but they're not perfect. And that's going to cost us a bit of quality. Okay, why are they going to be inaccurate sometimes? Well, let's say I've got two of my interesting intersections, two of my intersections where I'm going to make pickups or delivery or drop-offs are on opposite sides of the 401. So if I just take what the travel time I estimate between these is based on geometric distance, I'm going to say these things are right beside each other. So you should definitely, if you go to one of them, go into the next one right away is a good idea. But the real travel time is much higher. Okay? The real travel times we have to go around in a circuitous way to get across the freeway and get back to where we went. So if we instead just took the geometric distance, 300 meters, divided by, say, the average speed limit in Toronto, let's say that's 60 kilometers an hour, it's going to underpredict this distance a lot. That's not going to make us get an illegal answer or anything. It just may lead us to misoptimize the delivery order somewhat. We think going from one of these intersections to the next is a really good idea. Maybe it's not such a good idea. Okay, so this might be a hard question. Let's see if anyone can think of an answer to this. If I can, let me see if I can get rid of this. There we go. Okay, so we have the pathfinding algorithm you're running in milestone 3, and it's not going to be fast enough to get everything you want. We could use geometric distance, but it's not perfectly accurate. Is there anything else we could do? It might be pretty hard to answer, but I'll pause for a second to see if anybody can think of anything. So I'll give you a hint. Could we pre-compute all of the travel times that we're ever going to need? And all the travel times we're ever going to need is basically from our interesting intersections are a subset of what's in a city. It's the ones where we have pickups and drop-offs or depots. Those are the only ones we care about. How long does it take to get between them as we're optimizing delivery order? So could we pre-compute all of the real delays between those intersections? And then as we're optimizing our delivery order, we can now just really quickly look them up. Now, I already told you that if you just use your milestone 3 pathfinding algorithm, it's not fast enough to do that pre-computation, right? I have essentially n squared. If I have n deliveries to make, I have n squared times a constant. Interesting intersections, paths between intersections. I have like 2n interesting intersections, so that means the number of combinations is like 4n squared. I can't call my find path algorithm for milestone 3, that many times and still meet the CPU time limit we put on you for milestone 4. So is there anything else you could do to pre-compute all of these travel times between these interesting intersections? And this might be a hard question. I'll give you a couple more hints, but just in case anybody just already knows an idea, I'll give you a chance. Okay, so let me give you a few more hints. So yeah, we're going to try to pre-compute all of the shortest paths we might need as we evaluate all of our delivery orders. And this technique has has a name actually because it's used so much in computer programming. It's called memorization. Like you've got some data you're going to use all over and over again. Instead of computing on the fly, compute it once, store it in some data structure, look it up. So you actually did this in milestone 1 for a bunch of things. So can we do it again? Let's say we have some way to fill this in, but a reasonable way to store this data, we can store it in essentially a matrix, okay? We can store it in a matrix, we can store it in a hash table, there's a few ways to store it, but the idea is I have some from intersection going to some to intersection, and I could store, well, what is the travel time from, interesting intersection 1 to, well, let's say interesting intersection K to interesting intersection 1. This entry in my matrix will give me that number. If I want the travel time from intersection 1 to intersection K, it's down here, and so on. So there's an entry in this matrix for every single travel time. If I have let's say 200 intersections that are involved in my pickups and drop-offs, this matrix would be 200 rows by 200 columns, and it would give me all the travel times between those things. Okay, so that's one way I could store it. I could also store it in a hash table if you prefer, where the key is a combination of the source intersection, and the destination intersection. That would work too. So I know how to store it if I could fill all these numbers in. But how do I fill them in fast enough? Because the straightforward way is just call my milestone 3 pathfinding algorithm, but I got to call it, for n rows and n columns. That's n squared calls that I already went through. That's going to take too long. Okay? Well, I think I do it again here. So if I basically say we've got 200 deliveries to make, then let's see, actually I think there's 100 deliveries to make. Okay, so if I make 100 deliveries, and we're going to give you some problems that big, I need to call that my find path function from milestone 3 almost 40,000 times. I also want the delays to depots, so there's a few more calls still. If I add all that up, I've got something like, for a big problem, maybe over 40,000 calls to find path. Pretty fast find path is about 0.1 seconds. So this is over 4,000 seconds, and we're only giving you 50 seconds in the milestone 4 timeout. So can't do it. Okay, but there is a trick we can use to make this more efficient. So what you wrote in milestone 1, well, milestone 3. Let's say I want the travel time. I want the travel time between all these red dots. These are my pickup and drop-off locations, right? So those are my interesting intersections where I need to be able to quickly figure out the time between them. So I could use my milestone 3 algorithm. I'm going to use Dijkstra's algorithm. So I start it, say, at this intersection, and I run it for a while. It does this wavefront. It eventually finds this other intersection here. I trace back the path, and I can store what the travel time was. So I've now got one of the entries from my matrix. Okay, does this picture give you an idea of how we might do this faster? What's killing me, basically, is this is n squared. I have to do n squared invocations of my find path algorithm, this Dijkstra algorithm I just showed you, okay? Because I need, each one of them is giving me exactly one travel time. So now, does this picture give you any ideas of how I could tweak this algorithm so that I can make this, for this problem, where I want to fill in this whole matrix of delays, can I make it faster? That's probably as many hints as I can give without just revealing it. So I'll give you a second to think about this. If anybody's got an idea, go for it. And if not, I'll tell you in a second. So any thoughts? Well, maybe I can give you, so C10. I'm going to go to you. What do you think we could do?
I'm not really sure, but can you do while we are waiting out, and you don't stop when you find the first intersection. You stop when you find all the solution to all the intersections?
Yes, so that's perfect. Come see me after class. I'm going to give you a tasty chocolate bar. So that is a perfect answer. What I know at this point is I actually don't just know what the minimum travel time was, from this source location to this destination. I actually know the minimum travel time to every node in this circle, right? That's how Dijkstra's algorithm works. And there's a reason I'm using Dijkstra's algorithm here instead of A star. Dijkstra actually is more helpful to me in this case. So at this point, if I just stop when I found this intersection and I invoke my traceback routine to get, okay, well, what was the travel path and what's the travel time, I basically have thrown away all of the work I did to find the shortest travel time to all these points in this circle. So I shouldn't do that. If I, instead of stopping when I hit that first interesting intersection, I just keep going, okay? So I just keep going. I hit that interesting intersection and I can invoke my backtrace routine. So I can record, hey, here's the travel time to this interesting place. Here's the path I used to get there. But I just keep going. I don't stop the algorithm. I hit some more, and as I hit every one of these, I basically invoke my backtrace algorithm and I get what was the travel path, what's the minimum travel time. Or maybe I'll just run Dijkstra's until it's gone through the whole graph and then I'll just invoke the backtrace algorithm, n times. Doesn't matter, right? Code it either way you want. But basically, I can just run Dijkstra's algorithm through the whole graph, or equivalently until I've touched every single interesting intersection, but that's pretty much going to be the whole graph. So it'll work out about the same way, either way. And then I just invoke my backtrace routine from every single other intersection that was interesting. And what this does is it basically can fill in an entire row of that matrix with one call to this slightly modified Dijkstra algorithm. Okay, does that make sense? So I'll pause there for a second. Okay, so what you're writing in milestone 3 is actually called a single source, single destination pathfinding algorithm, right? You start at one node, one intersection, and you find the shortest travel time to one other node, one other intersection. But there are actually other variations on shortest path algorithms, and one that's very useful to us in milestone 4 to get a bit more quality is called single source to all destinations, okay? So we want to get the shortest travel time from any delivery location, pick up or drop off, to any other one. So, and with a single source to all destinations algorithm, which is basically just a small modification on the Dijkstra algorithm that you already wrote, right? Don't stop when you hit the target intersection, because there isn't just one target intersection. Keep going till either you've explored the whole graph, it's one option, so the wavefront is empty, or keep going till you've hit every single target intersection. That also works. They're going to work out to be about the same speed. If I do that, then every single call to this new variation on Dijkstra's algorithm, as I said, gets me an entire row of my matrix. It gets me from this one intersection to maybe 200 other interesting intersections. I get all those delays at once. So that's hugely less than what I had to call before. So I'm going to call this new pathfinding algorithm for a big problem maybe 200 times instead of 40,000 times. I also need to get the path from any depot, right? Because I want to choose which depot do I start at as well. So, but that's a small number of calls too. So I just start at a depot and I run this same algorithm and I, in one shot, find the shortest path to every delivery location. And then I also want the delay from every delivery location back to the depots, but I can actually get this, in this same call, right? I can just consider the depots to be other interesting intersections, and I'll do my Dijkstra's algorithm for the whole graph, and I'll just get from this starting intersection, what's the minimum delay to every depot as well. So if you add all this up, for a big problem, 100 deliveries, 10 depots, this is 210 calls. Okay, so let's try to figure out, is this fast enough? So first, is everybody with me? Like, do you understand how this algorithm is now, instead of having n squared calls to our find path algorithm, we just do n calls, or order n calls, to this new, somewhat modified pathfinding algorithm. Is everybody with me on that? Okay. So now we need to work out, well, what's the complexity of this pathfinding algorithm? We just made a different one. So how complicated is it? Well, I guess first let's go through. I'm going to say we have, I'm going to use the variable now k for how many interesting intersections we have. And I'm going to use the variable v for how big is our graph, right? I don't want to use n anymore, because if I use n to mean two different things, it's going to be super confusing. So we use k for how many delivery locations, so it's on the order of 200, and V, how many nodes in the street graph, that's on the order of 200,000. And I'm going to write a loop like this. For every one of my interesting intersections, one of my pickups, drop-offs, depots, I'm going to basically invoke this new pathfinding algorithm that I'm going to call multi-destination Dijkstra. And I'm basically passing into it, here's a list of all the intersections that are interesting. Well, actually, I'm going to pass into it, here is the ID, like the intersection ID of my start point. Okay, so I'm trying to get the first row, I want to start from my first interesting intersection. Maybe that's intersection ID 5000, I pass into my algorithm, that's the starting point. And it's going to go basically fill in one of those matrix rows for me. Got it? Okay, so first thing is we go through this loop k times. So that's the big win of this multi-destination algorithm. We don't go through k squared times, we just go through it k times. Once for every starting intersection that is interesting. Everybody with me? Okay, so in order to get the total complexity, I need to work out, well, what's the complexity of multi-destination Dijkstra? Because I need to multiply that by k. So we already, if you think back a small number of lectures, we actually worked out what is the complexity of Dijkstra's algorithm in a street graph. Turns out A star is the same complexity. So if you remember A star, they're both the same. A star is only faster by a constant factor. Does anybody remember, well, thinking back to that, what do you think the complexity of multi-destination Dijkstra is? So you can either just work it out, or maybe you remember what Dijkstra was and you get it from that. So I'll give you a second. Try to think about, what is the complexity of this? And maybe if no one's jumping up and down, I'll go on to the next slide. Actually, maybe I revealed too much on the next slide. I thought I revealed less with the animations, but I guess I screwed them up. So anybody have an idea what multi-destination Dijkstra would be? And it's not that hard to work out. Okay, so when we studied this, we said, okay, Dijkstra's algorithm, in the worst case, can search through the whole graph. But because we are using, we get to a node and we pull something off the priority queue, and we mark the node as either visited, or we can mark it as your best travel time is this. And that actually means we'll never look at it again. Okay, we won't have to actually update its travel time further. So because of the fact that we're going through our wavefront in an intelligent order, it turns out that we will only look at every node basically once. Okay, so because of that, let's see. We are going to basically go through V vertices, all of our intersections. We're going to put them into the wavefront. The wavefront is going to sort them. It's our priority queue. So it's logarithmic. In the worst case, we have every single node in the wavefront. In practice, it won't be that bad, but it doesn't really matter. Logarithmic's not very big. So we have V intersections that we're going to go look through. We won't do re-expansion. We'll look at them just once. And for each of them, we're going to look at it. We're going to do a bit of constant work looking at its neighbors. And then we're going to put that node, another node, into the priority queue, which is log V to put it in the priority queue. Then we're going to take it out. That's also log V. So Dijkstra's algorithm is V log V in a street graph like this. So the overall complexity is just we do that k times. So it's k, which that's maybe 200 if we're doing a delivery size of 100, times V log V. And that's actually not bad. Okay, I already told you your fine path algorithm, milestone 3, the good one's probably around 1/10 of a second. This algorithm will be a little slower, okay, because we can't use A star for this problem. A star uses this heuristic that says, am I getting closer to my destination or not? Well, now that I'm trying to go to 200 different places, that doesn't really make any sense. Right? I can't really use a heuristic to just explore towards some destination. I got to kind of explore in a circle again. And I'm going to explore pretty much the whole graph because I have 200 different intersections I'm trying to find the path to. Well, by the time I found all of them, I've probably gone through the whole graph. So those two things are going to make this a bit slower than your milestone 3 pathfinding algorithm, but not that much slower. So maybe it takes 0.2 seconds instead of 0.1. If I put in, a big numbers for this, like for 100 deliveries where we have about 200 interesting intersections, this means about 40 seconds. So you can do this in the time limit we give you. We give you about a 50-second time limit. So it's going to chew up a bunch of your time limit, but with this improved algorithm, you actually can pre-compute or memorize all of the travel times between these delivery intersections, and now you can use that as you're choosing orders to get essentially perfect predictions of travel time, which will help you choose a better delivery order. Does that make sense? Okay, so you don't have to do this. You could just use geometric distance if you want to keep it simpler. You will lose a little bit of quality, right? So, we benchmarked it, and you'll lose maybe 5% quality or so by doing that. So it's not catastrophic, but 5% quality on this problem is noticeable, right? So there isn't a reward for doing this in kind of the better way. But there's a trade-off. It's going to chew up a lot of your CPU time budget, so you'll have less time to sort of try different delivery orders. So it is going to chew up some of your time. Is everybody with me so far? The other thing I should say is this is not a lot of code change. So if you understand your milestone 3 pathfinding algorithm well, you basically make you make relatively small modifications to that algorithm, and you now have a version of this new algorithm where you go to multiple destinations. But it's not like a rewrite, it's add some stuff in. Okay, so one last thing you can do for milestone 4, but again, it's optional, is the machines that we have in the undergrad labs actually have, I believe it's 8 cores in them. So I'll tell you for sure in the tutorial. So you could actually use more than one CPU. One of the nice things about this problem, we're trying to fill in this big matrix, okay? Okay, let me go back to this matrix, see if I can get it. Okay, so I'm trying to fill in this big matrix, and basically I'm saying every invocation of that path search algorithm is going to fill in a row. So I could, if I had more processors available, I could basically launch that algorithm from multiple start points on different processors, and I could be filling in more than one row at once. So I have to go through a whole bunch of animations here again, so we'll go through this really quick. Yeah, so basically, in this loop, I have many calls to this multi-destination Dijkstra. There's actually no dependency between those calls. They're each computing independent data. They're each computing a different row of that matrix. So if I have multiple CPUs, I could actually do this work in parallel. And in the labs, you do have multiple CPUs. So this is a picture of an Intel processor, and the CPUs you actually have in the lab have, I believe, 8 cores in them, not 4 that I'm showing here. So you don't know yet how to multi-thread programs. Well, how many people have multi-threaded a program? Okay, so one person has. Okay, so somebody knows how to multi-thread it. It's an increasingly important topic. I'll talk about this in the tutorial, but basically CPUs aren't getting that much faster anymore per core for some important physical reasons. But you are able to get more and more cores because we can fit more and more transistors on a chip every couple of years. So what you do get when you get a new CPU chip is you get more cores. That has made it increasingly important to be able to take programs and say, let's try to use those other cores, because that's the main way that we're getting more computation nowadays. So what I'll talk about in the tutorial next week, that'll be like your last coding tutorial, is the basics of multi-threading. So how do we multi-thread a program in general? And then in particular, how will we do it for this parallel pathfinding algorithm? And I'll show you some gotchas and how to debug them. So we'll go through the basics of debugging a parallel program too. Parallel programming is fundamentally harder than serial programming. So if you think it's hard to debug a program right now where one thing's happening at a time, it's actually a lot harder to debug when there are multiple things happening at a time. So this is completely optional. You don't have to do it. You can get a good milestone 4 solution without it, but you can do a bit better if you use parallel programming, and you can learn a useful skill. So come to the tutorial next week to learn about it, and if you feel confident, you got some time, you can try it out in milestone 4. Okay, so that's it for getting better travel times. Let's go back to how do we get good delivery orders. Okay, so greedy algorithms are going to be pretty fast. Okay, like most of our work in a greedy algorithm is actually figuring out these travel times. So we either do that with geometric distance or we memorize it with this better pathfinding algorithm. But then the greedy algorithm itself is going to be super fast, like the ones that we went through last week. So we're giving you 50 seconds. You're going to find my greedy algorithm's done, and I got a bunch of time left. What do I do? Okay. So one way you can get more quality, and we'll call this heuristic 2, is something called multi-start. So we know our heuristics are not perfect. They make mistakes. So one way you can get a better algorithm get an answer from an algorithm that's imperfect is just run it multiple times, changing something. Obviously, if you run it, if you just do the exact same thing over and over again, you'll just get the same answer. So that's not useful. But we could run our greedy algorithm, and we just want to change something. We don't want to write a lot of new code. Just make it start somehow differently, make a different decision somewhere so we get a different answer. We have a function. You guys are going to write a function that basically says, what is my travel time for some delivery route? You see if this new one is better than the old one. If it's better, then you replace it. And you could do this now for a whole bunch of, you could do it many times because your greedy algorithm is actually so fast. And you can do this with any algorithm. Any algorithm that doesn't get a perfect solution, if there's some way you can perturb it and you've got CPU time, you can just run it over and over again and take the best answer. So this is used with all sorts of heuristic algorithms. For the greedy algorithm we talked about on Tuesday, look, how can we make it get a different answer? Like any ideas? So I don't write a lot of code. I just want to quickly make it get a different answer. So A07, what do you think?
There's no mic here.
Sorry, maybe I'll turn on A06. So this is the challenge with high-tech rooms, is they're sort of gradually degrading, right? So if you come back in like 30 years as alumni, you might find there's a cracked screen and one little screen over there or something.
We can start in a different place.
Start in a different place. Okay, so that's a good idea. And I guess we started on some depot. What we were doing is we said, let's take the depot that has the shortest travel time to some pickup. And you're saying, don't do that. Do something else. So what do you want to do?
We can start at like the very next one, like the one that has the next shortest travel time compared to the first one we found.
Yeah, so it's a great idea. So before we were starting at the, so we just make it force, that's actually the number one on my list, force it to start at a different depot. So we were starting at, the depot that was closest to some pickup. Let's start at the one that's second closest. Or, with this algorithm's so fast, maybe we'll just try it starting at every single depot. But that's a perfectly reasonable way to do this. And again, it's very little code, which is nice. Now after you've tried every starting depot, so maybe you got 5 depots to start from, you've tried all of them, okay, that was 5 times you ran this, but you might find, well, I still got a bunch of CPU time, what do I do next? You can do other things that are easy to code. You could say when I find what is the next intersection to go to, the way we coded this on Tuesday was always go to the next pickup or drop off that is legal, that has the smallest travel time. Well, you could say I got a 90% chance of going to the one with the smallest travel time, but a 10% chance of going to the one with the second smallest. And you can get probabilities using random number generators inside of a computer. Okay, so if you go to c++.com and you do a search for random, it'll give you a bunch of random number generation functions. So you can basically say, give me a number between 1 and 10, and if it's 10, I'm going to choose the second slowest or the second closest intersection, and if it's anything else, I'll choose the closest. If you do this at every single decision point, well, now you've actually expanded your decisions that you can make a lot. If you run this algorithm over and over again, it's going to make slightly different decisions each time, which will lead it down different paths. So you'll explore the search space this way. Does that make sense? So yeah, you can use this with anything. It's very little code. So that's what's nice about it. Okay, so this is just visualizing that. So here was my heuristic 1++, which was start at the depot that's closest to some pickup. Go there, and then just go to the next legal intersection. So it could be a drop-off. Here I went to a drop-off. Could be another pickup. So next I go to another pickup. Then I go to drop-off. And then eventually I got to go back to the depot I started at. I could try, if you look at this, there's a fair amount of backtracking. So maybe it's hard to tell, but this isn't the best answer. even with just 2 pickups and 2 drop-offs. So I can try again. I'm going to force it to start on a different depot. So I start over here, go to the closest pickup, closest legal thing turns out to be another pickup. Then closest legal thing is a drop-off, another drop-off, and then I go back to my initial depot. And visually, you can probably see there's actually less backtracking here. So even though I made my first decision didn't look quite as smart, my final solution actually is better, because it's difficult to predict just from your first decision, is this actually, how is this going to work out? Again, this would have been very little code to write, and I get a better answer. Okay, everybody with me on multi-start? So it's a useful thing to have in your toolbox. Can be combined with basically any algorithm. Okay, third heuristic we can use. So greedy algorithms basically make decisions and never reverse them. So they're always the greedy algorithms I've shown you are essentially building up a solution piece by piece, and only at the very end do we know what the whole solution is, what the whole travel order is. But at that point, we can't change anything. We've made all our decisions. So that can be inconvenient. So another class of algorithms are called iterative improvement. What that means is they take an existing solution, so you can actually feed a greedy algorithm into an iterative improvement algorithm, but an iterative improvement algorithm can look at the whole solution and basically just try to tweak parts of it, right? Try to improve things. This is kind of like agile programming. It's like, I've got a solution, now just see are there things that you can do to make it better. So let's say I have this solution. Okay, so I start at a depot, I go to a pickup, drop that off, pick up something else, pick up another thing, drop off A, pick up C, drop off B, drop off C, and then go back to the starting depot. So there's a possible solution to this 4 delivery problem. I'm going to stop drawing the city maps. I'm just going to draw like edges now. Annotated with the travel time, just to make the display less cluttered. I mean, all of those delays come from paths in the city, but I can abstract them just to delays. I've pre-computed all these delays. All I care about when I'm optimizing delivery order is the delay. Okay, so I'm just drawing that same thing, but without the city behind it, and I'm just marking the travel delays on it. So this is a representation of the path I just showed you. I started a depot, 2 minutes of travel time to my first delivery, pickup, then 4 minutes to the drop off, then 5 minutes to the next pickup, and so on, okay? And I go through all my deliveries in a legal order, and I eventually come back to the original depot. So the travel time for this is 93 minutes. Okay, so iterative improvement basically makes a local perturbation. Like if I just threw this whole solution away and tried again, that's really multi-start, because I'm not making any use of this solution, I'm just doing it again. So iterative improvement doesn't want to throw away this whole solution. So generally the solution has been created by another algorithm, or we've already optimized it for a while, so we think it's pretty good. We don't want to destroy it, but we do want to try improving it. So a local perturbation, there are many different local perturbations you could do, but one would be, let's take 2 of my deliveries, or 2 of my intersections of my delivery order, and let's swap them. Okay, so right now I go from B drop-off to C drop-off. That's the order in which I explore things. I could say, well, let's reverse that. Okay, keep everything else the same in the delivery order, but let's just reverse the order of these 2 things. So if I do that, let's see. I'm just trying to draw the edges. So I used to go from the C pickup to the B drop-off. Now I'm going to go in a different order, from the C pickup to the C drop-off. Okay? So, and I'm going to go from the B drop-off to the depot. So I've changed my delivery order by basically swapping these 2 intersections. I need to check, in the way we've given you this problem, you have to check now, is this legal? Okay, so you change the order of 2 deliveries. We can't drop things off before we pick them up. So we have to check in this new order, do we try to do that? Because that's not legal, I should throw it away right away. Okay, when I check this, I see, oh, I picked up C before I dropped it off, and I picked up B before I dropped it off. So it's still legal. So it's okay. Because it passes my legality check, I now want to know, well, how fast is it? Because I want to see if this is a good thing to do or not. So you're almost certainly going to want to write if you write an iterative improvement algorithm, you want to have a function where you give it a delivery order and it tells you the travel time. And we can use all the techniques we talked about so far to, to compute that. So I want to compute these new travel times. So I marked on the edges, let's say these are the new travel times. I looked them up in my matrix of pre-computed travel times, and I add all this up, and it turns out the new travel time is 85. So this is better, so I want to keep it. So I'm going to update my delivery order to this new one. And if it wasn't better, I would just throw it away. I would say, okay, don't make that perturbation. But there are many different ways I could perturb this. Like if I'm swapping the order of two intersections of my delivery order, there's a lot of potential swaps I could make. So I'm not going to try just one of them. I'm going to have loops that go through and try all sorts of perturbations and keep the ones that are good. Does that make sense? Okay, so that perturbation was swapped to, swap the order of 2 points in my delivery order. So just take two things and change where they are. We can make other perturbations. So we can make a perturbation that is a bit more powerful, it changes more. So one of the perturbations that works well for traditional traveling salesmen is something called a 2-opt. Okay, so what a 2-opt does is it makes a bit of a bigger change than just swapping two deliveries in the order. It basically cuts your delivery order into 3 pieces and then basically rearranges the order of those pieces. So it's a bit like swapping delivery orders, but it's not just swapping two intersections of that order. It's basically exchanging entire pieces of the delivery order. So the way you can think of that is it deletes 2 of the edges in this path, right? So a path is a connected sequence of edges. So I have a path that starts at this depot, goes through all my deliveries in a legal order, and comes back to it. So I'm going to delete 2 connections in it. And my code would, have to pick which 2. And probably what it would do is just try all sorts of options. You make this code fairly fast. You try to make this code fairly fast, and what you can do then is just try lots of perturbations. So my code tries, say, this perturbation. So it makes those 2 edges go away, and then it has to reconnect things in a different order. So let's say it reconnects the path in this way. So this implies a different order, and I have to reverse some of the arrows, and I have to fix up, oops, that's a stray animation. So I have to reverse some of the arrows, and I now get a new path. Let's see, reverse some of the arrows, fix up the depot connections, and I get this new path, okay? And I can work out all the delays on it, and let's say it was 72 minutes, so it's better than what I had before. Okay, so this is a more complicated perturbation. You'd have to probably think about this one a little bit. I'll talk about it a little more in a few slides. So yeah, it's not quite as easy to code, but it's still maintaining most of your prior solution because it's cutting it into pieces and reconnecting the pieces in a different order. That's fundamentally what it does. So I told you this works very well for classic traveling salesmen. For our problem, though, we have to check one more thing. We have to check if the path is legal. When we deleted those edges and reconnected the path in a different order, maybe we now have pickups occurring after, or drop-offs occurring before their pickup. That's illegal. So if that happened, we have to throw it away, or we have to fix it. Okay, so if you look in the literature, you'll see that 2-op works very well for traveling salesmen. It's a very powerful perturbation operator. For traveling courier, it works okay, but it's not quite as good, or it's got a few more problems because of the fact that it can make a lot of illegal solutions that you have to throw away. Okay, so let me go on and illustrate that maybe another way. Okay, so let's say this is my solution right now. Okay, so I start on this depot, and I go through these intersections that represent pickups and drop-offs in this order: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I go back to my original depot. Okay, so if I look at this, and I'm thinking about local perturbations that might improve it, I've got a couple of long travel times, right? So I'm going a significant distance from this intersection to that one, and I'm doing a significant distance again from intersection 6 to 7. So it looks like maybe I could improve this delivery order because these are, you know, significant drives across the city. You know, maybe that's wasteful. Maybe I can reorder things. So let's first try swapping the order of 2 deliveries. Let's say that's the perturbation operator that I wrote. That's the first one we looked at. Okay, so I want to swap the order of 2 deliveries. Maybe I choose this one and this one. Okay, so let's swap intersection 2 and 3. Okay, so I'm going to go to 3 first, then I'm going to go back to 2, then back to 4, then to 4. Okay, so what I did is I just changed the order of 2 deliveries in my delivery order, and the 2 I chose were, let's see it again, were these 2. Okay, so I swapped them. Does that look better or worse? What do you think? Does that look like a better travel route or a worse travel route? Okay, so it looks worse. So I made things worse. Now, the power of local improvement is you try a lot of perturbations, you only keep the good ones. So I can try other ones, but it turns out if I try other ones, with this structure, none of them will make it better. They all look like this. They, instead of having these sort of 2 long drives, I just wind up with 3 long drives, right? So I'm in what's called a local optimum. Like, this is a pretty good travel path, and a small change that just interchanges the order of 2 deliveries cannot make it better. So that's called a local optimum. So maybe that's the best solution possible, in which case I shouldn't worry about it. But there actually is a better solution. So let's say we'd used a different perturbation operator. Let's say we use 2opt. Okay, so 2opt, once again, it doesn't just exchange the order of 2 deliveries. It basically disconnects a couple of edges, so it cuts your path into 3 pieces. So now my path is in 3 pieces, and I reconnect it in a different way. That's what the perturbation does. There are actually a few different ways to reconnect it, so your code could try all of the ways to reconnect it. But let's say I did it this way. Okay, so let's say I connected 2 to 6 and 3 to 7. Okay, so if I do that, it's actually not really any better, okay? In fact, it looks a bit worse. So that didn't work out. But that wasn't the only way I could reconnect things. I could also reconnect, 2 to 7 and 9 to 6, and that actually does look better. Okay, my code needs to understand that by doing this, this part of the path needs to be reversed for it to make sense. Okay, so I got a little more code bookkeeping to do. And I also have to fix the, whoops, I think I missed that one. I shouldn't go to that depot, I should go over to here. Okay, so I need to fix up my depots. But in the end, this is actually better. Okay, so this more powerful perturbation operator is able to get me out of this local minimum. But just ignore that. I should have connected it up over here and removed this edge. Okay, and trust me, visually that looks a bit shorter because I drew it to make it represent a better travel time. Okay, so with a more powerful permutation operator, you can get out of local minima better. And let me kind of summarize that a bit. Okay, so there are actually a lot of different permutation operators that you can make for this problem. And if you do iterative improvement algorithms, you will get better results if you, generally, if you come up with either a good perturbation operator or even better than that, you try multiple ones, right? No one perturbation operator is kind of the best all the time, so if you actually make a few different ones and your algorithm tries them all, that's probably the best choice of all. Basically, 2ops I showed you can get you out of local minima. They can make a bigger change, but a lot of them are going to be illegal because of the fact that you have to do these pickups before drop-offs. So you might take that into consideration when you're proposing perturbations. You might say, I want to make 2ops where I'm cutting my path into 3 pieces, but I'm going to make one of those pieces pretty small. And that's the part that I'm going to have to reverse the order of. So maybe I'll make 2ops, but I will try not to kind of disconnect the path into 3 equal pieces. I'll try to disconnect it into 2 big pieces and 1 little piece, and it's less likely to be illegal. You could re-legalize. So the basic reason you have to throw away 2 ops is that you have a pickup occurring after the drop-off. Well, you could have code that says if that happens, let's try to fix it up. Okay, so we're gonna change the delivery order some more to move some drop-offs, move some pickups so that it's legal again. Your goal would be to do that pretty quickly. You don't want to spend a lot of CPU time because iterative algorithms are more powerful if they can try lots of perturbations. So you want them to be fast. You also want to re-legalize in a way that kind of disturbs the solution not too much, right? If you re-legalize in a way where you just say call a greedy algorithm to redo everything, well, your iterative improvement algorithm really is not perturbing anymore, it's just throwing things away. So that's the challenge of re-legalization, but it can work. You can basically find things are a bit illegal. I'm going to fix up just those part of the paths instead of throwing it away. You could also come up with your own perturbation operator. So 2-opt is one you'll find in the literature if you go read papers about this. But because we have these extra legality constraints, that might give you ideas of like, well, maybe I shouldn't use 2-opt. Maybe I should use something that's a little more clever and less likely to make illegal operations. You can also make 3-opts. 3-opts are basically, instead of removing 2 edges, cutting the path into 3 pieces, you remove 3 edges and cut the path into 4 pieces. And again, for classic traveling salesmen, this works pretty well. It's more powerful, gives you more choice. But we have even more chance of this being illegal in our problem, so it may not be worth the effort to code. And you also have more choices to explore, right? As you start saying, I'm going to chop up this path into 4 pieces, there's actually a lot of ways to do that. So maybe you don't have enough CPU time to explore them all anyway. You could also go to smaller perturbations, right? So swapping 2 deliveries could work well for this problem. You can do an even smaller perturbation where you just don't even swap, you just move the order of 1 delivery. 1 pickup or 1 drop-off goes to a different spot in the delivery order. It's less likely to be illegal. So that's an advantage. Probably can compute it quickly. So you could go to these more limited perturbation operators, and maybe they work well too. And yeah, I think that was all I had to say on perturbation operators. The team that actually won, so I have to release the milestone 4 assignment today, but basically you're primarily graded on the quality of your solution against basically reference solutions that we post, okay? So just against a curve. But if you have a competitive spirit, for the top 4 teams, we'll give bonus marks and you get bragging rights. So the team that had the top solution last year used many perturbation operators, okay? So that was, and they have other things. I'm not going to tell you everything they did in their algorithm, but they combined every algorithm we've talked about so far, plus one that we're going to talk about next week that goes 1 step further. So they combined all those ideas. They had many perturbation operators. And one of your challenges when you have many perturbation operators, you go, well, which one should I do next? How often should I do this one versus that one? Do I just hard code all that? They actually read one of my research groups, so one of my papers, and actually found that we had done this in chip design by using reinforcement learning to choose which perturbation operators worked well. So they actually applied reinforcement learning to choose among their perturbation operators, and it did actually work remarkably well. And it was funny, in their final presentation with Professor Chong and I were actually the graders for, they actually cited this paper from me, and I was like, I never thought of applying that to this problem. So I was actually like very impressed. Okay, we're not going to teach you reinforcement learning, but basically there is a big literature in this area, and you can even find things from sort of related literature and apply them. Yeah, I guess the main thing I was trying to highlight here is for perturbation operators, there really isn't one, this is the best. There's like a wide space of this. There can be a lot of cleverness. Combining multiple ones can get a better answer than even one. Now, I realize everybody's also short of time, so you also don't have to do that, right? You can get a very reasonable answer by just picking subsets of what we talk about here and just implementing that. But if you want to go for the best quality, there's a big space that you can go off and explore. And that's all I had for today. Okay, thanks everybody.